Yeah, this is Lulu from Brown University. So in this talk, I will introduce the library DeepXDE for solving both forward and also inverse differential equations. So when we try to use deep learning for partial differential equations, PDEs, people have developed different approaches in the past almost 20 years. Some approaches can only be used to some specific PDE problem. For example, if we consider the domain of the PDE is like a square, its image-like domain, or if the PDE is parabolic, then we can use the Fermat formula to convert a high-dimension parabolic PDE into a stochastic PDE, or if the PDE has corresponding variational energy form. So these approaches are specific to some PDE problem. And there are also general approaches can be applied for any PDE. For example, we can use Cloaking type projection for the PDE. And in this talk, I will focus on the strong form of the PDE. Basically, that is the physics-informed neural networks. In this symposium, we have already had a few talks focused on this part. Yesterday, Marta's talk and Paris talk, and this morning, especially the Mazier's talk, and also Chris also mentioned this part. Just in case you missed all these talks, so I will give a very brief introduction of this methodology using a very simple setup called invisible cloaking. So in this project, let's consider we have electric field phi, which propagates from our left-hand side to the right-hand side, indicated by the arrows. And then next, let's consider we have a small circle in the blue color in this domain. And this part in this small circle, it has different permittivity, epsilon 3, which is different from epsilon 1 for the surrounding environment. Due to the existence of this small sphere, then we can see on the right figure, in the downstream, the electrical field is perturbed due to the existence of this object. And in this invisible cloaking, we try to add another layer, which is in the pink color, surrounding this blue region, such that by special design, this epsilon 2, such that the downstream electric field, as shown in the red figure, looks like unperturbed, which means if we measure the electric field in the downstream, we cannot know whether there is objects in the upstream or not. So this is the setup of this problem. So mathematically, given epsilon 1 and epsilon 3, and also given the location and the size of these two circles, we try to find epsilon 2, which is a function of x coordinate and also y coordinate, such that the phi 1, which is the field, electric field for the outside domain, which is unperturbed, which means phi 1 should be equal to our phi 1 target function. So this is the measurements we have for phi 1. And we try to, from these measurements, to infer what's the correct corresponding field of epsilon 2. And as we know, this problem can be described by the Helmholtz equation, as shown in here. The Laplacian phi I plus epsilon I k squared phi I is equal to 0 for 3 different regions: the outside region, blue region, and also pink region. And also we have the boundary condition for the outer circle and the inner circle. So for each circle, we have the continuity of the phi 1 and phi 2, and also the normal derivative of partial phi 1, partial n, and the partial phi 2, partial n should be proportional to epsilon 1 and epsilon 2. So this is the PDE and also boundary conditions we have. So next, we try to combine the information of the measurements for phi 1 and also the information of the PDE here together to infer what is correct field for epsilon 2. And as I mentioned, we will use physics-informed neural networks for solving this problem. The basic idea of physics-informed neural networks is very simple. We will embed the PDE into the loss function of neural networks by automatic differentiation. So let's look at the figure here, which is a sketch of this method. Let's consider first we have a standard network, could be feedforward network, could be ResNet, or other types of network. So for the input of the network, it has two parts, the x coordinate and also y coordinate. So these are two scalars. And the output of the network includes 4 different fields, phi1, phi2, and phi3, which are 3 different electric fields on 3 different domains. And more importantly, the last output is epsilon 2, which is our target electro permittivity field for the pink region. So the key part is to design the loss function. So the loss function includes a few different components. The first component is the standard supervised learning. So because we know phi1 should be equal to phi1 target. Phi1 target is our measurements. So this is the standard supervised learning loss function. And next, we will add the loss function for the PDE into the network. For example, because for the outside region, for this outside region phi1, it should satisfy this Helmholtz equation. Then we can select randomly a few different locations for the outside domain and then evaluate what's the value for Laplacian phi1 plus epsilon 1 k square phi1. So ideally, this term should go to 0 to satisfy our PDE, but initially, definitely it does not. So we add this term again into the loss function. And the good thing here, when we use neural network, is that we can use automatic differentiation to compute this the derivative of phi1 with respect to the x coordinate and also y coordinate. So this Laplacian term can be computed exactly. And similarly, for phi2 field and the phi3 field, we have the same loss function. And also we can compute this loss function for the boundary condition in a similar way. So combining all these components together, the total loss function is a weighted summation of each terms. Then we minimize this loss function by training the network to learn what is phi1, phi2, phi3, and also what's the epsilon 2. So this framework is very simple and easy to understand. And also you can see, essentially we are solving the inverse problem of a PDE inverse problem. Then what's the advantage here? So the first advantage is that this method is mesh-free and also it's even particle-free. So we can bypass the process of drawing the mesh. It's really time-consuming to draw all the meshes. And more importantly, pins can seamlessly integrate the data information and the information of PDEs or other type of physics, like momentum conservation or mass conservation. And also in this paper, we show that by using some technology in deep learning, this framework can be easily to be used to handle the PDEs with black box boundary condition, initial condition, or black box forcing terms. Or even the initial condition or boundary condition has a very large noise. We demonstrate that we can handle up to 20% noise on these terms. So it's very robust to handle all the noises.
So just a quick question, what do you mean by black box boundary conditions or initial conditions?
Yes. So usually when we solving a PDE, we know the exact formula of the boundary condition and the initial condition. Then we can draw the mesh, and we know all the mesh points on boundary and initial. But if we only know the boundary condition or initial condition at some location, on some scattered locations, which is already there, we cannot modify. Then if we use the standard find element or find difference, we have to at first do an interpolation of the boundary condition or initial condition to have the whole field for the initial and the boundary. Then we can draw the mesh to have the value on any locations. The black box means we only have the values at some scattered points rather than the whole field. Yes. Then the fourth point is that this framework can be easily be extended to other types of PDEs. For example, integral differential equations. fractional PDE, or stochastic PDE. All these different types of PDEs can be handled in the same framework. Of course, we need extra techniques and methods, but the big framework is the same. So there are a few advantages of this method, and the method is simple itself. So after the training of the network, the red plot is the permittivity of this inner region learned from the network, with the correct corresponding electric field with showing in the left figure. So this is the method. It's easy to understand. And next, we try to have some understanding of this method. So usually when we try to understand a deep learning framework, there are three approaches we should investigate, including approximation, optimization, and generalization. So first, for the optimization, so we know that neural networks can be used to learn any continuous function if the network size is large enough. So this is guaranteed by the universal approximation theorem proved lots of years ago. But here, we added the PDE information into loss function. Then the first question is that whether or not if we increase the network size, we can always find a network such that the loss function goes to 0, which means whether the loss function, including the derivatives of the network, can also go to 0. And this is true, which is proved by Pingus in 1999. Basically, this theorem shows that the network can not only be used to approximate a function, and it can also be used to approximate the partial derivatives of the function simultaneously. So this theory is much more powerful than the standard universal approximation theorem. So this is the first question. So we know that the loss function of the network can go to 0 if the network size is large enough, ideally. And then when we have the loss function with the PDE in it, then what's the optimization behavior? And here, I try to use two simple examples to show that by using the PDE into the loss function, then the training behavior or the learning mode of the network would be totally changed. Let's consider two very simple cases. The first case is we used a standard network to learn a function which is fx is equal to a summation of 5 terms. As you can see, this fx has 5 different frequencies. So we do the standard C+ learning. We sample some data points from this function and train a network. Then let's look at the figure A, the left figure. So we have 5 frequencies of this target function. So during the training of the network, we do the Fourier analysis on the network output. And we investigate each components. For example, let's look at the first frequency. When the color turns red, which means on this specific frequency, the network matches our target function. So as we can see, for the first frequency, it requires almost 2,000 iterations to make sure the network matches the target frequency. However, when we go to high frequency, for example, the last one, then roughly it requires 20,000 iterations. So as we can see from this figure, the network learns from low frequency to high frequency. So this is for the standard approximation of 1D function. And this behavior has also been observed in image classification problem like ImageNet, as shown in these two figures, in these two papers last year. So this is true in general. But if we consider the pins, let's solve a Poisson equation with exactly the same function as the first one. So the solution of the Poisson equation is the same as case A. Then we can do the same thing. We can look at the right figure. The right figure is a training procedure of the network on this Poisson equation. Then as we can see from this figure clearly, all the frequencies are learned almost simultaneously, rather than from low frequency to high frequency. So in these two figures, we can see by adding the PDE into the loss function, the training trajectory or the learning mode of the network would be totally changed. So this is our numerical example. We do not have the theoretical theory yet. But for numerical examples, we can see how this training or learning of network be changed from the pins.
So I'm sorry, can I just clarify? So in A, you just train directly the neural network on your function, whereas in B, you use spin to calculate the f of x?
Yes. For A, for A, I use a standard network to train fx, some points, the standard supervised learning. And in B, we use pin to solve the Poisson equation. And the solution of this Poisson equation is the same as the solution of the first equation. Yes.
Okay.
So the solution are the same.
Thank you.
Okay, then let's move next. So as I mentioned before, when we try to use pins for solving a PDE, we have to evaluate the loss function on some locations sampled from the field. A naive way is that we can use uniform points of the domain. It works in many cases. However, these uniform points may not be efficient for some PDEs. For example, let's consider Burger's equation. Because the Burger's equation, the solution of the Burger's equation is very sharp around the point x equal to 0. Then if we use the uniform points, then we need lots of points to achieve a really good accuracy. So it's computational not efficient. And here we try to propose a new method such that we can efficiently use less training points to achieve a relatively good error. The method that we propose is called residual-based adaptive refinement. The idea is very simple. It's very similar to the adaptive refinement, mesh refinement in the finite element field. So the idea is as follows. When we train the network, we can adaptively add more and more points on the locations where the PDE residual is large. For example, we train the network on 1,000 iterations. Then we check what's the PDE residual on the domain on lots of points. And then we select those points with large errors as our new training points. Or in the deep learning field, in deep learning community, this method can be called as active learning. And here I draw two figures. So for example, in figure C, there are few crosses. These cross points are the new added points during the training. So as we can see, this method can automatically figure out where to add the new points. Because around the x equal to 0 in this sharp region, we should add more and more points. So this framework can automatically figure out we should add more points in this domain. And as a comparison, if we use uniform residual points to achieve the same accuracy, we need 10,000 training points on the domain. But if we use this adaptive way, we can reduce number of training points from 10,000 to 2,000 roughly. So here I give a brief introduction and some understanding from different angles for the pins. And in the second part of this talk.
Just a quick question on the adaptive training there.
Yes.
Have you looked into using generative adversarial networks for improving this training? Because I mean, that would be the standard technique for figuring out where a neural network is most likely to be incorrect, right? And so if you have something that's only most likely to be incorrect, that might be a nice way for building an adaptive algorithm.
Yes, yes. Actually, this idea has already been used in finite element mesh refinement. We haven't used in our framework yet, but definitely it's a good way to investigate. Yeah, that's right. Yeah, so in the second part of this talk, I will give a brief introduction of the usage of DeepXDE. So in summary, in DeepXDE, solving differential equations is no more than specifying the problem using the built-in modulus. So as we know, a PDE problem should be defined from the geometry, the equations, and also boundary initial condition. And then when we use networks, we need to specify what's network, what the size, or what's the type of the network. So in the following examples, I will show you how easily we can use DeepXDE for solving different types of PDEs. By only specifying these components, then all the remaining part will be done automatically by the software. The first example is a very simple time-independent problem, Poisson equation. Let's consider a Poisson equation on a 2D domain in the L shape with 0 boundary conditions. So the first line, we need to define the geometry of this Poisson equation, which is a polygon. So we can use DDE.geometry.polygon to define the polygon domain. So geometry is the modular in DeepXDE that handles all different geometries in 1D, 2D, and 3D. Then we need to define what's the PDE we try to solve by automatic differentiation. And the only grammar here we need to use from TensorFlow is tf.gradients. So tf.gradients would compute the first order derivative of the network output with respect to the network input. So for example, we can use tf.gradients yx. So let's go back one line. So in line 1, we need to define what's a PDE. So this x is network input and y is network output. So then we can use tf.gradients yx to have the first order derivative. Then we repeat this again to have the second order derivative. And we combine the second order derivative of y to x and y, this to match the notation, this should be du dx and du dy. So this is the Laplacian term and -1. So this is the residual of the PDE. So we can define the PDE using tf.gradients. Then next we define what's the boundary condition. So the boundary condition could be Dirichlet, Neumann, Robin, periodic, or even a more general boundary condition defined by any type of equations. So we need to define the boundary condition, we need to specify two things. The first, what's the location of the boundary condition? And next, what's the values for the boundary condition? For example, for the Dirichlet boundary condition. And by default, DeepXDE would use the entire geometry boundary as the boundary condition of our PDE. Of course, you can change which location to be the boundary condition. For example, I only want to my left part of my domain to be my boundary condition, or I need to define some partial part of my boundary to my boundary condition. So, as default, it will use the entire geometry boundary as boundary condition. And next, we need to specify what's the value for the Dirichlet boundary condition. And then we combine these two together into DDE.Dirichlet BC. So we have the boundary condition. So in this slide, we define what's the geometry, what's the PDE, what's the boundary condition. Then next, we combine everything together into another class called data, which is the virtual data for our PDE. So we define our DDE.data.pde as the geometry, was PDE, was boundary condition. And then we specify how many training points we try to use inside the domain and also on the boundary. Then next, we select what network we try to use. For example, if we can use the feed forward and we can also use ResNet or other types of network. Here, I use a fit-for network as an example. We need to specify what's the size is 4 hidden layers with 50 neurons per layer. And the activation function is hyperbolic tangent and with the colorate uniform initialization method. Then we compile this model with data net using the Adam initialization method with the learning rate 10 to the minus 3. Then we say, okay, let's train the network with 50,000 times.
So just a quick question, the compile, is it the static thing in TensorFlow or what is it? Static graph?
Yes, so in the compile thing, it will build the TensorFlow static graph and everything for the training.
And so if you use the Eager or if you use PyTorch, no, you can use PyTorch or?
Oh, currently this DeepXDE only supports TensorFlow, but as a future work, I still consider to use PyTorch as one backend. Yeah, so yeah, so here, these a few lines, as you can see, basically it's very simple. You just combine everything together and specify some values for the training, for the network size, and so on. And as you can see here, there are lots of dots here for each component. Was the data, was the net, and was the training, because DeepXDE currently supports lots of useful techniques. For example, for the compile, by default, we need the learning rate was the optimization method, but we can say more. For example, we need to say, okay, we try to use the learning rate scheduling. We try to decrease learning rate during the training, or we will do the early stopping. Once we monitor the learning rate decreased to our threshold, we should stop. Or if the learning rate never changes by some magnitude, we should stop. So everything here, there are lots of features can be selected by the users. But the slides shown here is the main part. Then after training, we can see for this L-shaped boson equation, the pin can achieve relatively good error compared to the true solution from spectral element. Then we go from time-independent problem to time-dependent problem. Let's consider a diffusion equation in 1D space, and also 1D time. There are only 3 components are different from the previous problem. So first, the geometry is time-space domain. So besides to define the space domain as an interval from -1 to 1, we need to define the time domain to be from 0 to 1. Then our space-time domain is just a cross product between our space domain and our time domain. So in this way, we can very easily to define the space-time domain. And then we need to define the initial condition. So to define the initial condition is almost exactly as what we do for the boundary condition. So by a few lines. And then we define the data by combining geometry, PDE, boundary condition, initial condition, and specify what's the number of training points inside the boundary, inside the domain, on the boundary, and also on the initial part. So as you can see, when we go from time independent to time dependent, basically everything is the same, except that we need to define extra geometry. Then in the third example, we will go from one different equation to a system of different equations. For example, here I consider Lorentz system, which is an ODE system, as shown here. The only difference of this problem is that when we define this PDE, currently we have a system. So if we need, for this system, we need 3 components of this equation or of this problem. Each component is corresponding to one equation on the Lorentz system. So we have 3 residuals returned by this function. And similarly, we need to define 3 initial boundary conditions, one for each component. Yeah, that's it. for this ODE system. The next problem is we go from PDE system to integral differential equations. So as I mentioned before, this framework can be very easily to extended to the integral differential equations. And here I show you one example, how can we solve integral differential equations using DeepXDE. Let's consider the Volterra IDE as defined here. The right-hand side is the integration with the kernel, exponential kernel. Then to define this problem, first we need to define what the kernel for the integration is exponential. Then by defining this kernel, then the software would automatically construct a corresponding matrix. Basically, it's an integration matrix for this integration kernel. So this matrix will be constructed automatically. Then we can define the right-hand side for the integration, which is the matrix times this y vector. Then for the left-hand side, it's exactly the same as previous. We use tf.gradients to compute the left-hand side, the derivative. Then we combine the left and the right to our IDE problem. And here we also have the data, we have the kernel, we have the IDE. And here, as I mentioned, the software will automatically construct this kernel, or this matrix, integration matrix. And inside the software, we use the Gaussian correlator for the integration. So you need to specify what's the correlator degree. For example, we use 20 degree. And after training, we can see we can successfully solve this Volterra IDE. And the last example is inverse problem. So we go from forward problem to inverse problem. And as you can see, we only need a few lines for defining and solving an inverse problem. For example, let's consider a diffusion reaction system. And the diffusion coefficient D and this reaction coefficient Kf are unknown to be learned from our measurements. So because D and Kf are also variables to be trained or to be learned, then we define Kf and D as Tf.variables before we define this PDE. So this is the first step. And in the second step, we need to tell or we need to input all the measurements into this framework. For example, we have some measurements for the Ca, basically concentration of this A component. We know the measurements of Ca at some locations observe X, and the corresponding measurements is observe Ca. So these are our measurements. Then basically we use two extra lines by defining these measurements as a special type of initial boundary condition. So basically we just copy paste these two lines. Then we can define these measurements inside our DeepXDE framework. And everything is exactly the same as what we did previously. Then we train the network, and we can monitor what's the value of D and what's the value of Kf during training. And after a few iterations, we can learn the D and Kf successfully. So one feature of DeepXDE is that it can automatically handle very complicated geometry using the technique called constructive solid geometry. So in DeepXDE, here are a few primitive geometry already defined, including 1D interval and 2D triangle, rectangle, polygon, disk, and also cuboid. Cuboid and 3D cuboid and sphere. So these are a few geometries in 1D, 2D, and 3D already defined. And also we define.
Yeah, sorry. Can I ask a question here?
Yes.
So regarding the boundary conditions, I mean, in the pin, this is typically so it goes in the loss function and so on. So it sort of feels that, for example, let's say you want to apply Dirichlet boundary conditions.
Yes.
Well, the user could just specify points and values for the solution at those points.
Right.
So so my question is, you know, why do you need to have this support, you know, to describe the geometry and so on, rather than just having the user specifies, you know, just coordinates of points?
So first, if the geometry is complicated, for example, for the geometry showing here, we try to solve this problem solve the PD problem on this geometry. Then if we manually define all the points, then basically we need to define the points along these 7 different segments. It's time consuming. It's doable, but especially if we try to go to 3D, if we have some complicated 3D geometry, then we need to try to specify or manually choose the locations on the geometry. It's boring and time consuming. So here I try to give a very easy way to select what's the boundary condition on the geometry. So basically makes the user so easy to do, easy to define the problem. So the ways we first have a few standard geometry. Then we define 3 Boolean operations: union, difference, and intersection, and showing in this left figure. If we have the A is a rectangle, B is a circle, then this union is A, basically is A plus B, and the difference is A minus B, and the intersection is a region between A and B. Then for any complicated geometry, we can easily construct this geometry by the simple polygon, circle, and then rectangle using the 3 standard operations. So that's why, as you can see in the previous example, the user only need to define what's the boundary condition and basically what the locations are in the boundary condition. And by default, all the physical boundary conditions are in the boundary condition. So then the user can save time by selecting all the points on the boundary, especially for this type of complicated geometry.
So quick question here.
Yes.
So when you're representing it, for example, let's say you use a sphere, are you still going to use a 3-dimensional neural network, or are you going to reparameterize it to be 2 dimensions on the sphere, right? Are you using the manifold coordinates, or do you have to use the Riemannian coordinates?
For the sphere, basically the input is X, Y, and Z. Oh, you use what the coordinates? Currently, I use the standard coordinate.
Mm-hmm. And then do you just have to make sure that you sample when doing the training process, you're just sampling from the sphere? Or is there more that needs to be done in order to make it so that way it's only learning on the sphere, right? Because it's a more general 3-dimensional object. I guess it only needs to satisfy the PDE on the sphere, right? That's the condition you're holding?
No, so here the sphere means we have a PDE defined in the sphere. So boundary condition is on the surface of the sphere, but we have also PDE inside the sphere.
Okay. Okay.
Yeah. Yeah, it's not it's 3D, not rather than the 2D manifold in the 3D space.
Okay.
Yeah, it's true 3D. Yeah. So as I demonstrated from the 5 examples, to solve a problem using this DeepXDE, the users need only define what the geometry, was the equations, what the boundary condition, initial condition, and select what's the neural network. And there's no redundant code. So then the user do not require to select where is the training points manually. So then the code is really short and comprehensive. And the user also do not require know the TensorFlow. So the only TensorFlow grammar the user requires is the TF gradients. And currently, DeepXDE support almost all useful techniques in deep learning field, especially when we use deep learning for solving PDEs. For example, we can use dropout to do the uncertainty qualification, or we can do the early stomping, or we can dynamically saving and loading network. There are many useful techniques has already been implemented in the software. So roughly all the techniques we require in practice. And even if the current software does not satisfy your new requirements, for example, you have some very specific requirement, like yesterday in Paris talk, he has a new idea of neural network which is not implemented in DeepXDE yet. Then it's very easy to do because the framework of DeepXDE is very structured and highly configurable. Each component can be, so the user can insert a very small piece of code in each component and it will work. And there are also a technique called callback, which means during the training, without going into the details or without modifying the inside code of DeepXDE, the user can plug in some code to modify or change the behavior of the training using a callback mechanism. And also, currently, DeepXDE supports a few other functions, like the multi-fidelity learning we proposed in this paper, and also learning nonlinear framework we proposed in this paper. So there are extra functions. The software can be installed by either pip or conda. And also here the websites for software. And welcome for reporting any bugs, suggestions, or pull requests. Yeah, that's it. Thank you.
Okay, thank you very much for this presentation. So we're quite a bit behind schedule. So maybe one or two questions.
I have a question. When you use this software to solve forward problem, yeah, because in traditional methods, you need to, for example, for time-dependent equations, you need to care about stability, like CFL condition and things like that. And in your framework, you do not let the users choose the scattered points. So do you have any mechanism so that you choose the correct scattered points to guarantee the stability or convergence?
Yeah, actually, this is a good question, I would say. So the stability and also convergence of this methodology of pins is still an open question. So we have numeric examples to show that, in fact, we do not, for example, for some PDE, usually the standard numeric methods, we need a CFL condition. But in pins, we do not exactly CFL condition, but it still works. I'm not sure why. So this is the open question. So
I think
answer for it.
I think that there is an answer to that, because you're not actually evolving things. You assume that u is a function of x and t. So you learn a function of x and t, and then if you want a later time, you evaluate it at a later time. So this does not give you any trouble with stability, but at the same time, it's restrictive, because if you want to go into times which are out of the domain on which you trained, you cannot. So I think it's explainable why you don't have an issue, because you actually learn a solution. You don't learn an evolution operator.
Yes.
That's right. Yeah, that's right.
I mean, look, if you look at your setup, you learn u of x and t, right? You don't learn how to go from one time to the next. So there is no problem with stability, because you don't actually have to evolve something by iteratively applying it like you would do, let's say, with an Euler method or with any method to solve a PDE.
Yeah, there's no time step.
Yes, there is no time step here.
Yeah, but the information is still.
Yes, but you learn the representation of the solution in a domain, a spatiotemporal domain, x and t. You see here what you picture.
Yeah,
so
but if
yes,
but during the training, the information is still propagates from the initial condition to a longer time, right?
Yeah, well, I mean, but it's
But what
the
do you mean
information is
propagates? Because
propagated.
if I give you the solution at time 0.5, you don't have a way to tell me, you know, how to go from 0.5 to something else. You learn the representation of the solution of the PDE in the whole domain, spatiotemporal domain. I don't see any evolution in your setup.
Yeah, I mean, so this pin method is more just familiar with, or more similar to things that are fully implicit PDE solvers, right? So if you look at some of the old control theory literature, you'll find stuff about fully implicit discretizations, and they have similar. I mean, they have really good stability properties for similar reasons. And then I think that where you'd probably find most of the proofs here are probably with people who've used radial basis functions for solving partial differential equations in a very similar way. And there have been some stability proofs, and it really does come from the fact that it is fully implicit. But I agree there that then if you learn a fully implicit discretization, then you cannot necessarily evolve it beyond the bounds that you placed in the first place. Yeah.
Yes. Because think of it, I mean, you specify the domain of t to be 0, 1, you specify the domain of x to be -1 and 1. So if I ask you for the solution at t is equal to 2, you have to actually retrain, because your solution was, I mean, the representation of the solution was learned inside this spatiotemporal domain. So if you want to predict the value of the solution outside of the, let's say, the time of 0, 1, if you go to 2, it's like trying to do extrapolation, and you know that neural networks are not good at extrapolation like that.
Yes, that's true.
Yeah. So I think this is why you don't have basically a stability constraint.
Yes.
Okay, thanks. Yeah. Any other questions? Or so actually, I had a question about, you say only the TensorFlow knowledge, but you need to define your neural network and so on, right?
Yeah, but the network is already predefined in the software.
But say you, well,
So the user
definite,
only,
okay.
yeah, user only need to call these functions. That's it.
And then why don't you let the user define the neural network in TensorFlow?
It's doable. So as I mentioned here,
I see. Okay. Yeah.
this module can be easily extended by the user. So for example, the user on a new network, that's basically define apply to the software. But we a few standard networks.